So the pressure in a fluid is proportional to how deep you are in the fluid, and I'll show that by just doing this simple example. This is a beaker full of water, and the height is h and the area is a. Then the pressure at the bottom is just the force on the bottom divided by the area, right? And that's just equal to the weight of the water divided by the area. And so the pressure at the bottom, we'll just call it pressure at the bottom to simplify that a little bit, is equal to mg divided by the area, right? And we're just talking about the pressure due to the water, right? The water in here. And so the mass is just equal to the density times the volume times gravity divided by the area. But the volume is just the area times the height, right? That's what the volume is. And so the pressure at the bottom is equal to the density times the area times the height times gravity divided by the area. Those areas cancel, and the pressure at the bottom is equal to rho gh, right? Rho is the density of the fluid, g is gravity, and h is the height. And so the farther down you go, the greater the pressure gets in the fluid. And so, if this is a centimeter, if this is a centimeter or 0.01 meters, the density of water is 1,000. So 1,000 times 0.01 is 10, times 10 is 100. And so if you were a centimeter deep in water, you would have a pressure of 100 pascals on you. If you're at 10 meters depth, you have about 100,000 pascals on you, and that's about 1 atmosphere. It turns out that the actual pressure is higher because the atmosphere is also exerting a force on this. But just in terms of the pressure due to the water, this is the expression. So this is just a little bit on atmospheric pressure. In the last example, we talked about the variation of pressure with depth. That discussion assumed a constant density. If the density is varying, then the discussion I gave isn't quite right. And it's okay to assume a constant density in liquids most of the time because they don't compress very much. They're like marbles already up against each other. In a gas, it's a little trickier, but over small distances in a gas, you don't get much variation. The one example we encounter where there is some variation in density is like when you're dealing with the atmosphere, which if you go 100 miles up is very thin, and you go at sea level and it's at its most dense. And so you have to be a little careful about dealing with large distances in gases. But for most of the cases we'll be assuming constant densities. And so I just want to talk for a minute about atmospheric pressure. So atmospheric pressure is basically the weight of the air all the way to the top of the atmosphere, out into the vacuum of space over any given area. And it turns out that depending on what units you use, it's 14.7 pounds per square inch. So if I made a little square inch on my whiteboard here, like that, say, call that a square inch, and I could cut the column of air out all the way to the top of the atmosphere and weigh it, it would weigh 14.7 pounds. Or if you remember, a pascal is a newton per square meter, there'd be 101,000 newtons if this box was, instead of a square inch, a square meter, right, really big, all the way to the top of the atmosphere, there'd be 101,000 newtons of air. That would be the weight of the air in that. You get the same weight in 760 millimeters of mercury. A column of mercury a little over 3/4 of a meter high would give 14.7 pounds per square inch. Another name for that unit is torr, after a guy named Torricelli. I can't think of his first name. He was Italian. He was the first guy who really figured out that the pressure of the atmosphere decreases as you go up. Nobody really knew that, and he built a barometer, which we'll talk about, a manometer, and walked up a mountain with it and showed that the pressure was going down as you got higher in the atmosphere, which led scientists to believe that the space is a vacuum. The atmosphere is also sometimes called an atmosphere. So we've got pounds per square inch, pascals, millimeters of mercury, torr, atmospheres, bars, So 1 atmosphere is 1.01 times 10 to the 5th Pascal. It's also 1.01 bar, and so you might be able to surmise that 1 bar is 10 to the 5th pascals. A torr is 1 millimeter of mercury. All of these are units that are used in various fields to measure pressure. It just depends on if you're biology or medicine or physics or engineering. The one we'll use the most is probably the Pascal, since it's the SI unit for pressure. So we can talk about the pressure in a liquid, including atmospheric pressure. If, for example, I have the cup of water I had earlier, right? I can say the pressure in the liquid, just due to the liquid, at some depth h, is pressure is equal to rho gh, right? But if I want to include the atmosphere above it, then I can say, well, look, the pressure at this point is just P0, which is equal to 1 atmosphere. And so the pressure here, P is equal to P0 plus rho gh. This includes the weight of all the air above plus the weight of the water down to this point. This was just for the water. Often we'll just be interested in this number, neglecting the atmospheric pressure, and so this would be called the gauge pressure. The gauge pressure is a pressure difference, and it comes from the pressure gauges we use. Like if you measure the pressure in your tire, that's the gauge pressure. If your tire is flat, the gauge pressure measures 0. That doesn't mean there's a vacuum inside your tire. What that means is the pressure difference between what's inside the tire and atmospheric pressure is 0. In other words, your tire is at atmospheric pressure on the inside, which means won't hold your car up. And so the gauge pressure is just a pressure difference between inside and out. And so here, if you were looking at the gauge pressure, you would just be looking at the pressure due to the depth of the water and not the stuff, not the air. All right. So here's another example. We can say, what is the force acting on a dam that is 500 meters wide and 80 meters deep? And so, if this is my dam, this is going to be a weird drawing, but here's my dam, right? And so the water's on this side, right? Here's the water over here, right? And then the ground is over here, and so the concrete dam is just holding up against the water. This length here is 500 meters, and the depth here is 80 meters. And we want to know what the force is. If we look at it edge on, right, where this height is 80 meters, and there's my water, we can say, well, if we're just looking at the gauge pressure, then the pressure at the top is 0, right? If the pressure is rho gh, then the pressure at the top is 0, or the gauge pressure, and the pressure at the bottom is the density of water is rho g height down to the bottom that's 1,000 kilograms per meter cubed times 10 meters per second squared times 80 meters, which is 800,000 pascals, and that's the pressure at the bottom. So P bottom equals 8 times 10 to the 5th, right, pascals. And so the average pressure is just halfway in between. It's 4 times 10 to the 5th pascals, and that's the average pressure that the wall feels. And so the force is equal to the average pressure times the area, which is 4 times 10 to the 5th pascals, times the area, which is 500 meters times 80 meters, right? And so that's 4 times 10 to the 5th Pascal, which is in Newton per meter squared, right, times So 8 times 5 is 40, and so that's 4 times 10 to the 4th meters squared, right, which is 1.6 times 10 to the 10th newtons. And so that's the total force that you're going to feel at the that your dam's going to have to support. This giant force, right? A couple things to notice about that. First of all, the pressure at the top is very small, and so when you look at dams, they often are narrow at the top, but at the bottom the pressure is enormous. And so 1 meter length along the bottom, would have a much higher force acting on it than a 1 meter length on the top. If you look at public aquariums that you can go visit, and look at the large containers that hold things like sharks and stuff, you'll notice that the glass is wider at the bottom than it is at the top, because there's a much larger force acting at the bottom because the pressure is higher at the bottom. So this is a manometer, and a manometer is basically just a U-shaped tube where one side is attached to something whose pressure you want to measure, and the other side is open to the atmosphere. That's the most typical way it's done. And so the key here is this side is open to the atmosphere, and so that means at the top of the fluid the pressure is atmospheric, right? And then I can look at the difference in heights between these two across the column. So this is gas over here, and I want to know what the pressure is in here. And because this is a gas, the pressure is the same everywhere. That is to say, we don't have to worry about the variation of pressure with depth in a gas, because gases have such a low density that rho GH is really, really tiny across the height of the container. And so it's only when you start getting to stuff like the atmosphere where you can get to large enough distances that it starts to matter. But pressure does vary in a liquid because they're much more dense. And so what we said earlier was that the pressure varies with depth in the fluid according to rho GH, and that means that the pressure here, since it's the same, this is all the same fluid, the height of this is the same as the height of this, right? Then the pressure here is just the pressure at the top plus rho GH, where rho is the density of the fluid. Maybe it's water, doesn't have to be. And G is gravity, and H is the height below the surface. And so the pressure increases with depth according to rho GH, and so the pressure here is rho GH. And so that means that's the same thing as the pressure here. That's supposed to be a P. Sorry, this is a P, and that's a rho. And so you always, if I draw it like that, if I put a hook on it, that's a P. If I don't, that's a rho. Just rhos are densities, P's are pressures. I'm trying to be a little careful about it. And so the pressure here is the same as the pressure here. And so this is the pressure inside. The pressure inside is equal to the atmospheric pressure plus rho G times the height difference. Notice the height could be opposite, and so I'll draw one of those in the next example. But so here the pressure is higher than atmospheric pressure, and you can kind of see this. The pressure here is pushing the fluid down. So if they were equal on both sides, the fluid would be at an even height. And so the pressure here has got to be a little higher than atmospheric to push the fluid the other way. And this is sort of what Torricelli did. He just created this with at the bottom of the hill, and then as he walked up the hill, the pressure on this side was decreasing, and so gradually, as he walked up the hill, the height of the fluid shifted from the left side from the right side in this picture to the left, and he knew that there was a lower pressure here than here. And so as he went up the hill, he noticed that the farther he went up the hill, the height difference got bigger and bigger. So if the pressure is the other way, if this is at a lower pressure than the atmospheric pressure and the air is pushing down, you might set this up at the top of the hill and walk down, and then this would be at a lower pressure than when you got to the bottom of the hill. This would be a higher pressure. And so we say is the pressure at this point on both sides is the same, and this side is atmospheric pressure, and this side is P plus rho GH, where that's the height, and rho again is the density of my fluid. And so if I want to solve for P is the atmospheric pressure minus rho GH. In other words, this has got to be at a lower pressure than the atmospheric pressure for the column to be higher on that side. That's another manometer example. So this is a mercury barometer, and basically what it is a tube that's filled with mercury. The blue stuff is mercury. And so you take a tube and fill it with mercury all the way to the top, and then you turn it upside down in a pool of mercury, and so it looks like this, and it's supported somehow. Don't worry about that, or at least I won't worry about that. And what that means is that when you turn it upside down, it falls away from the tube a little bit, and the pressure up at the top, you didn't have any air in there, and so the pressure up at the top is pretty close to zero. It's actually the vapor pressure of mercury at room temperature, or whatever temperature it is at, but it's close enough to zero that you can call it zero, a vacuum, right? And by the same arguments we were making earlier, we can say that at this point, this is just open to the air, and so this is atmospheric pressure, and so that means that that P plus rho GH is equal to P atmosphere. And since P is zero, this just means that rho GH is atmospheric pressure, or the height of the column is the atmospheric pressure over rho G. And so if we evaluate that, we get 1.01 times 10 to the fifth newtons per meter squared divided by 13,600 kilograms per meter squared times 9.8 meters per second squared. And if you evaluate that, you get a height of about 0.758 meters. You can work that out. And so that height is about 0.76 meters, and that's why we say the atmospheric pressure is 760 millimeters of mercury, right? It's 0.758 meters. In fact, atmospheric pressure goes up and down, and so the height of the column rises and falls with the atmospheric pressure, and so by reading the height of the column, you can tell what the pressure in the atmosphere is. If the pressure in the atmosphere decreases, then the column drops. If the pressure of the atmosphere increases, the column rises, and so on. The reason why atmospheric pressure rises or falls has to do a lot of things, but if there's just sunlight, it hits the earth here. In areas where it hits the earth, it causes the atmosphere to expand outward, where it's hot. As gases heat. So the sun shines on the earth warms the air expands as it warms, and then it can just roll over to areas that aren't as haven't expanded as much, and then there's less air above you in some region, and that produces lower pressure. There's less weight above you, and so pressure varies for all kinds of reasons, but that's a typical reason. One thing you learn studying pressure in fluids and things like that and densities is geologists do a lot of cool work to figure out how the earth works, and these tools help them do that.